Hey, welcome. Thanks for joining. This evening, we're going to be covering, well, we're going to be doing a connect the dots session. So to kind of tie up at a high level all the different models that you've covered so far. So from KNN, logistic regression, all the way till decision trees. So we won't talk about random forests and boosting, but we'll just connect all the algorithms from KNN, logistic regression, linear regression, GAMs, all the way to trees, and kind of give you an overview. There was a question. Okay. All right. And so yeah, I'm going to take you through basically at a high level all of the models, what they're about, similarities, the differences, etc. So we won't really go too much into, well, we won't work with Excels and actual data, but if there's some specific model that you do wanted me to deep dive into, then I'll have to set up another session for that. I did post an announcement if anyone wanted kind of further clarification on any of the models, but I didn't get any. So I'm assuming everyone's kind of happy with their understanding, which is good news. I'm also happy to hear that. But yeah, just let me know otherwise. All right, so let me switch my camera off, and I'm going to share my screen instead and take you through all the models that you've covered so far and tell you how they fit in. All right, so we'll start from the beginning. And if you can't see my screen, please just let me know. Excuse me, apologize for my voice this evening. All right, so connect the dots. So far you've covered these models: linear regression, logistic regression, GAMs, discriminant analysis, KNN, which is k-nearest neighbors, and decision trees. Okay. So far, all of them are supervised learning models. Linear discriminant analysis can be used for both, but just note we'll kind of focus more on the context of it being used as a supervised learning algorithm. And what do we mean by supervised? Well, we're trying to predict something. We had some outcomes in the past, and what we try to do is we try to take some variables in and make a prediction on a y variable. All right, so what we're ultimately trying to do is we're trying to take some x variable. So let me just share my screen here. So we're trying to take some x variable, and that could be anything. Say we're trying to take salary, and we're trying to predict whether they would default on a loan, right? So if this was your salary, we're trying to map x to a y, right? Whatever we're trying to predict, default on a loan. Okay, so we're using this to predict that. And that's essentially what supervised learning is. All right, so let's go over linear regression first. All right, so on the flow chart, linear regression is what we're going to cover first. And it's essentially just trying to predict a continuous variable. So instead of your y, instead of it being category, your y could be you trying to predict what is the debt that they would have in a year. And so that could be anything, all right? Could be 50,000, 75 continuous values, and that's linear regression. So let's get to that. I'm sure you would have seen this equation when you covered linear regression, and you would even work through data to estimate these values in the equation. But what you're essentially trying to do is you have these data points, these circles, right? These are the actual data points that you have, and you're just trying to fit a straight line to these data points, all right? And I know some students get confused with the term OLS, or ordinary least squares. All right. What you need to know about OLS is the tool to determine this line. Okay, so linear regression is the process of fitting a line to this data, and OLS is the tool used to find the slope and the intercept for this line. And this line can be for more than just one variable. Here, it's just because it's easy to visually look at it when it's just a single x variable and a y variable. But often in practice, it's very seldom you actually have just one variable that you're trying to use to predict your y. Right? It's often a series of variables, like what you see in this equation on the top. So instead of just one x, you can have x1, x2, etc. All right, so that's linear regression. How do you determine the best line? And that's minimizing. So if you look at this line, there's a vertical distance between each point and the line. And what you're trying to do is you're trying to find a line that if you had to sum up the distances, these vertical distances between the point and the line, specifically the squared values, you want to find a line that actually gives you the lowest sum of that. And that is your SSR. In other words, your sum of your squares of your residuals. And that's just the sum of those vertical lines squared, right? And the line that gives you the lowest total, that's your best line. And OLS is the tool used to find that line. Okay, so let me just check the chat. The question so far. All right. And from this diagram, you can see the assumption that this model makes. It assumes that it can be a linear fit, right? So that's a big assumption that this model makes, okay? But in practice, you can find cases where, your data is linear in nature and you can fit a linear regression line. But you will have cases where it's not linear. And I'll get to a diagram that kind of illustrates that in a bit, all right? So just keep that in mind. It assumes that a linear relationship exists. All right. And so that's linear regression. Now, logistic regression, it actually should have a different name. It shouldn't be called regression because it does cause confusion. It should actually be called logistic classification because that's what it actually does. It doesn't predict a continuous value. It's the equivalent of linear regression, but it actually predicts a target class, okay? So a discrete value. So in other words, will this person commit fraud or won't they? Will this person fall into cabin A, cabin B, or cabin C in a cruise ship, for instance, all right? So categorical variables, and that's logistic regression. So here, this graph on the right, okay, if I'll draw your attention to that, let's say you have some variable, right, x. So that's shown in your horizontal axis. Yeah, we'll call it feature, but it's the same thing as x. And so what this graph is showing you that whenever this feature is a negative value, so in other words, the blue dots, then it belongs to a class 0, right? Whatever that class is, it may just be a number, but in the real world, it has an actual meaning, right? It could be that they don't commit fraud. That's what the 0 means. And the 1 means that they will commit fraud. So that's the red dots on the top, okay? And so what this feature is very good because it clearly splits them up. When that feature is less than 0, it's saying that that person is going to be a class 0, right? They don't commit fraud. And when that value of that variable is more than 0, it's positive, then it's saying that this person will commit fraud. And the model to do that prediction is a logistic regression model, right? This curve here, it's called a sigmoid curve. What a sigmoid curve does, it actually just returns a probability to you. So it compresses the output of the model between a value of 0 and 1, and you use that probability to assign the person to a specific class. Now in practice, and I did this in the random forest and the boosting session, you'd get a probability. So if you get a probability of 0.6, it could be left to you to make the decision, okay, anyone with a probability of more than 0.5. Okay, so if the probability is more than 0.5, we'll make that person a class 1. So in other words, we'll say that that person is going to commit fraud. But that can be changed to a different value, to your specifications. But this value is given to you by this curve, this black line, the sigmoid function. All right, and this model returns that value. So in other words, it actually looks at the log odds ratio. All right. So yeah, so that's logistic regression. And a model that's often used to compete with this is LDA, which you've done, I believe, with Nadia, linear discriminant analysis. And we'll get to that now. And I'll explain the differences between the two. Chat. Good. Okay. All right, so let's go to linear discriminant analysis. Now, okay, I'm going to come back to general additive models. Let's go to LDA. All right, so LDA, linear discriminant analysis. Now, there's no diagram here, so I'm going to actually kind of do my sketch here. Just give me a second. Essentially, what LDA does, it does two things. It can predict whether a data point belongs to a certain class, and it can also reduce the number of variables. All right, so let's look at a diagram that kind of can help conceptualize this. Find a line. Okay, so I'm gonna do my best to draw a vertical line here. Yeah. All right, so let's say we get two different classes, and I'm going to let maybe X represent one class like this. Right? So you can think of the X as the, you know, the 0. All right, so this, and then I'll let the other class be represented by circles like this. All right, so whatever these variables are, we'll call this one x1 and x2. All right, what happens is if you had to collapse this data, and what I mean by collapse is, let's say I introduce another line, and let's put it in a different color here. If I put this line here like that, and I collapse all these points onto this line, right? Then you're going to have something like this. You're going to have the x's here, and you're going to have circles pretty much sitting on top of this one, x's here, and then circles here. All right, so now when you have that, you can see that, yeah, the best kind of cut or stroke that you can make on this axis to separate them is somewhere around here, like that. But it's not ideal because you're still going to be getting some circles that fall into the X categories, all right? And you're also going to have this X here that falls into the circle category. So it doesn't clearly split the two, all right? So it's not ideal. And as you can see, this data is, if you look at your circles here, all right, they're very spread out. Look at the size of the circle end, right? It's very spread out. And the same with these X's here, quite spread out. Now let's change things a bit, all right? Now, instead of collapsing it like how I did here, let's collapse it this way, like this way. If you do it that way, then you're going to see a lot of your circles, like I'm pretty much mapping my circles to this line, like that. There you're going to get all your circles getting bunched up here. And then here you're going to have your X's sort of being bunched up here, right? Like that. And you can see that this would do a better job of splitting them up. And you're kind of concentrating them a lot better. And that's what LDA does. LDA does these two things. It maximizes the distance between these two classes, and it reduces the variance between them, all right? The scatter. That's what LDA does. And now this line that I've drawn here, you can use this as a single variable. We can call it Z if you want. And instead of using x1 and x2, we would just use a single variable. So you reduce the dimensions and you found a better way to separate the classes. All right, so that's what LDA does. It does two things. It can reduce the dimension and it can separate classes very efficiently by maximizing the distance between them and reducing the variance. Questions? Okay. All right. But there's some assumptions that LDA makes. Just ignore the square on the right, okay? You haven't done QDA. You're not going to do that. So I had it on my slides and I just decided to leave it there, but don't focus on it, right? You're only going to cover LDA, right? So don't be alarmed. LDA, it assumes that your distribution of data follows a normal distribution. Some of you may have covered the normal distribution when you did statistics. Some of you may not have covered it, but essentially what it's saying is that it's assuming that if you had your two classes, right, your X class and you had your circle class, if you had to draw a histogram for both of them, for each of these classes, they would be bell-shaped, perfect bell-shaped. That's what it's assuming. So it makes that assumption, whereas logistic regression doesn't make that assumption. All right. So LDA does something that logistic regression doesn't do. It also reduces the dimension or reduces the variables, and it can handle more than one class. So say there was another class that I introduced here, a tick. So maybe this is class 0, this is class 1, and this is class 2. Logistic regression doesn't do too well when you give it more than a 0 and a 1. But LDA does a good job at handling that. So you can give it more than just two classes, all right, for LDA. Another benefit of LDA is that for your number of data points, okay, so in your Excel, when you were working with data, you would have had a number of rows of data. When you were working with the IRIS data set, all right, you recall you were trying to predict the species of those plants, Setosa, etc. Your Excel had a number of rows. Now, the more rows you have, logistic regression prefers that. LDA, however, you can give it fewer rows and it can do a better job than logistic regression. So it can, if you have small data sets, if that's all the data you just have, LDA tends to do better than logistic regression for that. Okay, so that's what you mean robust when n is small. Okay. All right, let's go back to GAMS. All right. Now GAMS is, so the first model that we spoke of at the beginning of this session was linear regression. Okay. And let me give you a kind of a real world example to put things in perspective. All right. So let's say we were looking at the time of the day. Okay. So here, this is the time of the day. Time of the day here. And so let's just say it starts at 5 o'clock, right? We're just going to kick it off like a typical day when everyone wakes up. So 5 a.m., 6 a.m., etc., 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 all the way till, let's say, 8 p.m. Okay, so it'll be 20, 0, 19, 0, etc. All right. Now, let's say we were trying to predict traffic flow. Now, everyone here, I'm assuming, to have experienced traffic in a typical working day. As you know, in the early hours of the morning, it's kind of not so busy. So on the y-axis here, we've got volume of traffic. Okay, so your traffic flow is quite slow here, but as you get towards 7 a.m., the traffic starts to pick up. So it starts peaking, all right? And that's peak hour, and then it drops again. It's kind of quiet during the day, and then when you get to your afternoon peak hour around like 5 or 6 p.m. It starts picking up again, and so on and so on. Now, if you did this for a week, this is just one day. If you did this for a week, you'll continuously see this cycle up and down, etc. You get the idea. Now, if you were to try and put a linear regression model to try and predict this, it wouldn't do a great job, okay? Because this data does not follow a straight line. So if you had to put a straight line, it's not doing a great job. But for this kind of data, right, where you have wave-like behavior, GAMS does very well. Okay, GAMS can do a much better job at fitting this blue line than linear regression because it doesn't assume any linear relationship, right? And that's what the graph is on the slide on the right here. So your blue data, all right, this is another example. Your blue data points are not linear, they don't follow a straight line, but a GAMS model is the green line. And when you fit that to the blue dots, it does a lot better job at putting that data. Now, it does it in an additive nature. And what I mean by additive, it's similar to how you had your linear regression model, except for your linear regression, you didn't have this f in front of the x, okay? It was directly the x variables. But here, each of these f values is a function. So you're actually adding up a function of x1, a function of x2, etc., depending how many variables you got. And that is what gives it that flexibility. Often these f's, these functions, they're called basis functions, and splines are used, all right? That's a very common model that's used to fit the data. And the benefit of splines is that it doesn't need to make any assumptions about the data. It doesn't need to assume that it's following any sort of distribution. It just looks at the data and it can fit according to that. So it's often considered as being non-parametric. Okay, you don't have to. It doesn't have to have any pre-specified parameters in order for this model to work. Right, and that's what we mean by non-parametric. Right, there's no assumptions about the data being made when this model is fitted to that. Okay, and so that's GAMS. Let me check if there's questions in the chat. That was good. All right. Right, so that's GAMS. So let's go back to the beginning. We've done linear regression, okay? That's for a continuous variable. We have logistic regression, and that is for classification. We have LDA, don't worry about QDA. And then we have GAMS, all right? And GAMS, which we've just covered. I know you haven't covered it in this order. You actually did KNN right at the beginning, but it doesn't matter in the order in which we go through it now. Next, let's go to, I think we got KNN. All right, so KNN, the graph on the right kind of does a good job of kind of explaining it. So let's say you got two different classes. You got the stars in orange, and you got the other class, which is blue triangles, right? And they could represent maybe, bacterial infection or viral infection. Okay, so the orange is viral infection, and the blue dots is bacterial. And then you have this new data point, right? This pink square, and you need to decide which of these classes is it going to fall into. Is it going to fall under the bacterial or the viral? And so with KNN, what you do is you specify how many neighboring points you want to use to make a majority vote. So that's if it's classification. Right? Let's just assume it's classification. For this example, it is because you're trying to predict whether it's going to be in a viral class or a bacterial. So when you choose k is equal to 3, what it does is it calculates the distance for this pink dot, pink square, to every single point in the data set, all the points, right? There's different ways of calculating the distance. Euclidean is often used, but there's more than just one way, right? There's the Manhattan distance as well. But I think for now, let's just assume it's Euclidean. And you can read up on the different distant metrics that you can use. So it calculates the distance for every single point to the pink dot. And then it looks at which of those points, which are the 3 closest points. and that would be this one orange star and these two blue circles. Now, based on that, those are the three nearest points. So let's just draw like a proximity circle around it. Now, if you had to vote, where would this pink new point fall under based on a majority vote? You can see that there's more blue triangles, in other words, bacterial infections versus viral. So because of that, it would be classified as the blue circle. So the diagram on the right, if you follow the orange arrow, it's saying, okay, it's going to classify it as a blue triangle. And that's when you choose 3 as your k nearest neighbors. Now, k is specified by the user. Okay, the user needs to specify. So if you're going to run this model, you need to specify k beforehand. And sometimes you may ask, but what value do you choose for k? And it's not a easy, clear-cut answer. You definitely don't want to choose k as big as the number of data points you have, right? But you always want to choose k to be an odd number, right? Okay, so often in practice, when you're actually using k and n, just one guess will never be enough. It's very unlikely. If you did, well done. You kind of were lucky on that one. In practice, different values of k are experimented on. And what you would do is, if you look at my graph and I'm going to draw, you would have maybe k on this axis, and you would run this algorithm for a number of k's. So maybe k3, 5, let's say 99, right? And here on the y-axis, you would have your performance. So your accuracy or how good you did compared to the what the actual values are. And sometimes you could find that your graph would be, it looked like something like this. Something like that, all right? So from this, you could determine what the k is that you should be. So that's how often it's done in practice, all right? You have to run it through a number of k values. And to keep in mind, it's not done in Excel. So if you had to do this in Excel, it would take you forever. In the next semester, you'd be using Python or R to actually do it. And then you could actually work this out, right? You find the optimal parameter. That's what we're doing. It gives you the best performance. And that's the k that you would use. And if this k value is, let's say, 30, 33, and that's the value you would use. Okay. And so that's what the graph on the bottom does. It's just for a different k, and it shows how the results would change if you had to change your k, because now you have more viral infections versus bacterial infections in the proximity. And so the pink dot, the new dot, the new data point would be classified as a orange star instead. So k does make a difference. You can actually change the outcome. All right. So k nearest neighbors, it's often referred to as a lazy algorithm. And why it's lazy is because the thing is with k nearest neighbors, it doesn't really learn anything. When you give it training data, all it does is it uses that training data as a reference data set. So when you give it a new data point, all it's going to do is it's going to calculate the distance for that data point. So in other words, this pink data set, this pink point, it's going to get the distance from that pink point to every single point in your training data set. And then it's going to perform this operation that we just did. Doesn't matter what new point you give it, it's always going to use the training data set as the reference data set to make its decision. So you can imagine every time you give it a new point, it's going to calculate the distance for that from that point to every single point in your training data set, which is not efficient, and especially if your training data set is large. So here in this diagram, it's just a few points, you kind of understand the concept. But in practice, if your data set's like 10,000 rows, and that's 10,000 points in this chart, and it's not efficient. So like I said, it doesn't learn anything. All it does is just stores the training data set and just follows through a procedure to classify a new data point, right? So it's different. to how a decision tree is. And then I'll show you that in the next point, next slide. So just keep in mind, okay, so K, what you need to take away also from K is that when K is very small, right, then what you're saying is you're trying to fit it to every single point. So that's going to cause overfitting. You're going to get a high variance, all right? And when K is very large, right, almost the size of your data set, then you're going to underfit, right? So that's what you need to keep in mind, okay? Large K will underfit, small K will overfit. There's also something that, I'm not sure if you experienced it. From what I gathered, you haven't encountered it yet, but in practice, you can have data sets that are imbalanced. And what do I mean by imbalance? All right, let's just say this is your data set. You have a number of rows, okay? Now, say your target variable, or in other words, your Y, it consists of 0 and 1. Now, let's say you had 100 data points, right? 100. So you had 1 row, 2 row, all the way to the 100th row. What happens is sometimes you can only have a few cases where your value for Y is 1. You could actually maybe just have 10 of them, and the rest of them is 0. So here you'd have, let's say, 90 of them, but here you'd only have 10 of them in your actual training data set. And you can see that's quite an imbalance, right? That's 10%. That's only Y. And you often have this in the real world. You can have data sets like this, right? Where it's the target variable has only a small proportion of one class versus the other. And when you have this, KNN doesn't do very well, because as you can imagine, if the data set is this imbalanced, then when you're working on K nearest neighbors, it's always going to tend to move new data points to the majority class, just because you got more of them. So just think of this chart on the right. If you had a whole lot more blue triangles than the orange stars scattered all over this graph, and every point that you put in is likely going to fall under a blue triangle, just because it is the majority class. And that creates a problem when you tend to do predictions. You might not get any predictions that fall under the orange class. All right, so that's how KNN is affected by imbalanced data sets. Curtly, go for it.
Yes. Hi, Daryl. I just wanted to know, well, this is just for me to understand, and also just to maybe see your thinking. Maybe it could give me insight on the assessment itself that we got. I wanted to know, on K nearest neighbors, let's say you are calculating the Euclidean distance. Is it allowed for you to decompose the equation and then put it back together on the final calculation, which would be where you then calculate the square root of? So basically, for each point, you first find the squared difference for each variable. And then after that, you then find the square root of the sum of all the variables in your last column.
Yes.
According to my understanding, that would be decomposition of an equation, which I believe is mathematically correct.
Yes, it's perfectly correct. And sometimes people prefer that because you can it makes it easier to understand, one, and if you did make an error, you can pick up the error because the formula is not too bunched up. Like if you had every single thing in one column, if you did the difference, you had to do the squares, you do the sum, and then you do the square root all in one column. That formula gets quite busy. And so if there is an error, it's going to be a bit difficult to pick it up. But if you decompose it like the way you're talking about, that does also make it easier to pick that up. So you can do that. Does that make sense?
Okay. Yes. No, thank you.
No problem. All right. So that's K nearest neighbors. And lastly, let's do decision trees. All right, decision trees are, in my opinion, in my experience, it's very handy, very useful in most problems in the industry. And the reason being is because it's just very easy to visualize, and it does a decent job at doing predictions. So let's look at this data set on the top here. This graph that you're seeing here, you've got two classes, right? Class 1 is red and class 0 is black. Now, if you look at this graph, it's almost impossible to have one line that's going to clearly separate the black and the red points. You can't actually do it with this. Think of you running, slicing it with a sword in a straight line. There is no one line that will cleanly separate those two. And this is what we mean by non-linear data. So in the beginning, when I told you, you'd be fitting a straight line to data, that's when you assume a line can do a decent job, but here you can't be done. So what you want is actually to use a tree, because the tree can actually follow those blue lines that you see here. The tree can make these cuts based on the blue lines. So it can actually go horizontal, then it can go vertical, and then it can continue this way and do another cut vertical. It can partition it according to how the blue lines are. And if you did it that way, then you can see you can clearly separate these red and these black dots. And that's what you always want to do when you're doing a classification model, right? When you're doing a classification model, you're trying to separate the classes. You're trying to find rules that will clearly identify one class over the other, right? And when you have data like this, a decision tree does very well. Now, just note that in practice, like now, the visual I'm showing you, it's easy to see it when you just got two variables. So if you had x1 being age and x2 being your income, and you're trying to predict whether someone would take insurance or not, all right? So the black dots could be they don't take insurance, and the red dots is they do take insurance. So you're just using two variables to predict that, age and income. To visualize it like this, it's easy, right? You can look at this graph and you can see it's pretty simple to do. But once you start increasing the number of variables, then it becomes tricky. You can't visualize it. So it's important that if you can just understand it for a few variables, just so you can visually get the idea, then just keep that idea in mind when you extend it to more variables, because that's what you're often going to do in practice. You're going to very often use more than just two variables to develop a model. Okay. So here we've got these two variables, and then the tree is what you see in the bottom that actually creates these rules to say, okay, when x1, all right, when it's less than 2.5, so around here, all right, go this way, yes, and then it says, okay, that green box that you're seeing here, it's saying make that class 0. So the number right on the top of that box, that's a 0, so it's saying everything in that box is classified as a 0. So that's what this tree is doing. It's giving you the rules to split up these data points. So the parts of this tree is pretty much the blue lines that you're seeing here. It's separating the data set, following those rules to get as pure nodes as possible. So these boxes, these nodes at the end, right? You want them to have almost entirely just the one class. So having a pure node. And so that's how decision tree works. Nonlinear data, it's very easy to read. If you look at this tree, the rules are very easy to understand. Here, this tree, it has a depth of, I think about 3 here. So you count the number of nodes going down, and that would be your depth. All right. Often going more than a depth of like 5 or 6, it leads to overfitting. So you don't want your tree to go too far down and have too high a depth, because you can tend to overfit. And I'm pretty sure everyone knows what overfitting is, judging from the assignment explanation. It's when your model does very well on your training data set, but it does poorly on a new data set that it hasn't seen before. So when you increase the depth, that's what happens. when you go beyond 5, it can tend to happen. All right, that's one of the parameters of decision trees that can cause overfitting. Let me just check the chart. Okay. All right. Now, ensembles just pretty much use a whole bunch of these trees. Now, once you start combining more than one tree, you can easily just lose the interpretability. That means you don't get to visualize it like with this chart on the bottom. You don't get to have that flow diagram to explain how it came to its decision. But sometimes you have to ask yourself, okay, is it more important that my model gets the prediction right than me understanding it, or vice versa? You know, obviously in a perfect world, you always want a model that does very well at predictions and can explain the prediction. You know, to have both is a win-win, but sometimes there's a compromise between the two. And you have to decide, depending on the nature of the problem, what is more important. And maybe some of you might just think, okay, maybe the prediction is just important. I just want to get the prediction right. But in the real world, when if you're in the industry, think about it this way: if your model is to either decline a client for getting insurance or accepting them, the client has the right to understand why you have declined them. And so by that, whatever model you develop, you should be able to interpret it and provide the client a reason as to why the model has made that decision. Right? So sometimes some models are regulated in that it's constrained by industry standards that it has to be interpretable. It cannot be a black box model. All right. So the next chart kind of just summarizes everything. So we've covered pretty much all the models that we want to cover this evening. This slide just gives you a basic overview of the comparisons of it and features of each of these models. So linear regression, it's linear, it's a continuous value. If you're trying to predict house prices, etc. Logistic regression is a classifier, so you could use that for your iris data set. You know, if you're trying to predict Setosa and the different plant species. LDA, it's linear, but just like logistic regression, it also does classification, but it has another benefit is that it can reduce the number of variables, and it works better if you have a limited number of data points. Okay, if your sample size is small, if you have a few rows of data. GAMS can overcome most of the problems that linear regression has. So it can do very well at fitting to data that doesn't follow a straight line. Any wave-like kind of nature data, GAMS can do better at predicting continuous values when the pattern follows that kind of shape. KNN, right, highly irregular, not a very efficient algorithm, doesn't really learn anything from your training data set. It just stores the training data set, and every time you give it a new point, calculates the distance and then determines where it should fall. Remember, most of the problems that we were talking about were classification, but often it's when you want to change it to regression or predicting a continuous value, then let's just go back to KNN just so I can explain that. Instead of the predicting which class it falls into by majority vote, if you're using a regression problem, if you're trying to predict a continuous value, then this pink dot would just be the average of the orange and these two blue circles. It becomes the average of everything in that proximity when you're dealing with continuous values as opposed to classification. And the same thing for decision trees. All right, it becomes the average of everything in these nodes. Okay. Parametric. All right, so remember what I said about parametric? It's whether there's any assumptions about the data beforehand. And with linear regression, there is, you assume it's linear. Same thing with logistic regression, LDA as well, it assumes it's linear. But GAMS, there is also there's debate of whether it's parametric, but okay, just ignore that I have yes here. Consider this a typo and make this a no. Okay, GAMS is non-linear. So just if I can scratch this out, I would, but just forget this yes under GAMS for parametric, right? It'll be non-parametric. KNN, no assumptions about the data, and decision trees also makes no assumptions of the data. No distribution assumptions needed, and you can follow any nonlinear shape. Interpretable, linear regression and logistic regression are quite easy to understand. LDA is also, I would say it is an interpretive model. Medium, I just put medium there so you kind of understand it's kind of in between, but it leans more towards being interpretable because it is easy to understand. GAMS as well, you can understand it as well, all right? So it's medium to high, it is interpretable. KNN, it's not that easy to understand because you're just calculating distance to each point. If you need to understand why it got that prediction, you actually need to look at the points that were closest to it, and that's a lot of work. So it's not very interpretable, all right? All you pretty much know is that it's based on the distances from points that were close to it. Decision tree, very interpretable. Just by looking at this diagram that I showed you here on the bottom, it's very easy to understand why the model came to its prediction, all right? And then lastly, it's good when there's linear relationships for linear regression, as the name suggests. Logistic regression does well when you just have two possible outcomes for your target variable, yes or no, survive or not, take up product or not, all right? But once you have three classes, like your iris data set, logistic regression doesn't do too well, all right? LDA will do better at that. And like I said, it does well when you have small sample sizes. GAMS handles nonlinear nature of data, wave-like structure. KNN, it's complex local patterns. So what it means is basically, like you said, it's just looking for patterns around the training data set. So all it's doing is just storing the training data set, getting the distance for every point. It doesn't really learn much, all right, from your training data set. There's no patterns that's actually learned from it. And then decision trees, it's nonlinear and it can be easily interpreted. All right, and then this is the last slide. And here is just a summary of, whether they're linear, nonlinear, and parametric, all right? So you can ignore QDA, oops, no QDA, we're not gonna cover that. GAMS is nonlinear, as is decision trees, all right? GAMS, KNN, they all fall under non-parametric, and linear regression, logistic regression, and LDA, they all fall under linear boundary algorithms. I'll make this slide available, just like all the other sessions, and I'll make them available in ARCs. If you want to go through it, it's kind of just a summary and connection between all the different algorithms. Because from what I gathered, you've done a lot of the calculations and examples in the Excel exercises for the sessions and the tutorials. But if there's anything that's not clear, please, let me know. I hope this was insightful. And the floor is yours if you have any questions. Let me check the chat. Yes, yes, I will make the slides available. Who is first? Michael.
I think it was called logistical regression, and that was also a classification, just like KNN. Just more on how that works. I know KNN is the closest sample data, but just a little confused to how the logistical regression works.
Okay.
Like not the one that's the straight line, the one that's like either yes or no. Yeah.
This one. Is it this one?
Yes. Thank you.
Okay. So what it does is, essentially what you do is, let's say you have a few predictors here, right? And that when I say predictors, I mean features or X variables. So you've got your X1 and X2. So let's keep it simple as just X1 and X2. So this first box that you see on the left, you have just two predictors. Let's give it variable names. So we kind of not talking about just X1 and X2. X1 is age, X2 is income. And you're trying to predict whether this person will take insurance or not. So what you do is you have these two variables, and then you have a what we call a z-score that we fit to the X1 and X2. And what we do is, with that X1 and X2, for each of those values, each of those rows of data sets, if you remember how you do linear regression, right, you would fit this Y to x1 and x2 and get the best coefficients using OLS. That's the method that gives you those coefficients. It's the same thing here, but you're putting it to Z instead. All right, so it's the same thing in this first box here. All you're doing is the same thing as linear regression. But then once you have that Z, you're going to do something different now. This Z gets fed into this next block, the sigmoid function. So this black line that you're seeing, that's everything on the left-hand side of this equation for the sigmoid. That is that function. This S little curve here, this black line, that is the value in that equation, right? And that black line, all it does is it's giving you a value between 0 and 1. In other words, it's giving you a probability. When that probability is lower than 0.5, it's telling you that this point is closer to being a class 0 or a non-fraud case. And if it's above 0.5, then it's more likely to be a fraud case. And that's pretty much how you connect that Z to the probability.
Thank you. Very helpful.
No problem. No problem. Good question. I think there was another one. Or was it the same question? No, answer that. Priyanka?
Hi, Daryl. Yeah, I just have a question regarding the second assignment. I did went through it a bit, and I see there's a couple of questions that we did not discuss yet. So just curious to know if there's like maybe a roster or any plan that we can maybe get as students, just to see like when what is going to be discussed with us, so we can actually plan out when to answer which questions. And then also if we have questions that we actually raise it beforehand and not like 2 or 3 days before the assignment is due.
Yeah, so Bianca, I'm assuming you're talking about neural networks, SVM, which I think that's all in your assignment, and you haven't covered this yet. So that has been raised. Yeah.
Yeah, let me just open it. I think there's like 4 or 5 questions. Like question 1 is theory, that's fine. Question 2 is fine. Then question 3 and 4, 6 and 7. So 4 out of the 7 questions we can't actually answer yet.
Yeah. Okay. So I know there's offhand. I know there's 3 sections that you're being tested on that you haven't covered as yet. 1 is k-means clustering. 2 is SVM, support vector machines, and the third one is neural networks. So that's been raised, and we're trying to find out if they're going to push the assignment due date further to allow more time to cover those sections before the assignment. Don't hold me to it because I haven't got any feedback as yet. We're trying to figure out the best way to actually do it. And yeah, of course, we're not gonna try and cover this like a few days before the assignment is due. We do understand that that wouldn't be fair. So I'm just waiting for some feedback from the higher powers, and yeah, I'll provide it as soon as I get any information.
Thank you.
No worries. All right. Okay, I hope you enjoyed the session. Yeah, I did record it. I'll make the recording available by tomorrow, along with the slides. I'll post it on all. But thank you for joining. Yeah, I hope you're enjoying this course and you're enjoying the content. Yeah, we'll chat soon. Have a good evening, everyone.
Bye.